Start this recording. Oh, nice try, Emily. Oh, hey, nice. Don't worry, I won't be able to see you anyways, just for that brief moment. Okay. That, let me look at that. So last day, we started talking about, okay, what if we have a collection of sample proportions, for example, what would that look like? Turns out it looks like a normal distribution, and that's really nice because then we can find probabilities and things associated with a sample proportion. And then I gave you that pretty tricky Excel assignment. And so if you have questions about that, then we can talk about that later. But I think it's not due until next Sunday anyways, right? So you got some time. But yeah, I know it's a little bit tricky, but it's just meant to show you that, okay, if you know what the population looks like and you draw a random sample, and then you have your sample proportion, and then you do that 100 times over, then you have a collection of sample proportions, which is really just a numerical variable now, which is kind of like crazy, right? But then you can take the mean, you can find the standard deviation of this thing, and if it follows a normal distribution, which by the central limit theorem it does, then you can use z-scores and you can find probabilities. Pretty cool. Oh, excuse me. I'm just gonna remind myself of, okay. So we said, we introduced just the concept of inference last day. And so today I want to introduce the confidence interval, which is always kind of a fun one. And then on Wednesday, we'll do hypothesis testing, or we'll introduce the concept of hypothesis testing. It's quite a big concept, and there's a lot of ins and outs and rules of the game that we have to establish. But once we have them, we can apply them to any scenario, and that's really nice. So today, we're going to do confidence intervals. Maybe not colon there. So a confidence interval, we do use confidence intervals more or less just in everyday speech. So I think the example that I would have used is, okay, how far is it to my house? It's 4 kilometers, whatever, plus minus 1 kilometer, right? Oh, how confident are you? I'm 95% confident, right? Because there's a chance that my estimate was wrong and maybe my bounds are not capturing the true distance. And so we're gonna do that. We're gonna do that for any statistic. Now, there are some key ones that we're going to focus on. And so confidence intervals. And for today, we're going to talk about one sample proportion, p hat. And maybe I'll move this here. And I'll say today. Later, we'll expand this to any statistic, right? So this is a statistic or a point estimate. So we'll extend it to any point estimate. So that's kind of cool. So what I want to do is just introduce a confidence interval in general. And then when we introduce different types of statistics or point estimates, then I'll introduce the key components that we need to build this confidence interval. And then we've got it. So if we break down how far is it to my place, well, I start with my point estimate. I start with my best guess at the actual distance to my house. And so we start with a point estimate. Right? Just some value, in this case, p hat, right? Our sample proportion. And then we're going to go plus a little, minus a little, right? And so we're going to go down a little, up a little. And what we're going to move is we're going to move some critical value. And we're going to talk about that today. Some critical value times the standard error of the point estimate. This should be maybe I'll do this. Make it more obvious that those are two things being multiplied together. Yeah. And so in our case, right, let's do maybe green. For one sample proportion, our point estimate is p hat. Our best guess at what the population proportion is p hat. Now, plus minus, and I'm going to leave the critical value for a little bit because we don't know what it is. Although you do, but we haven't talked about it explicitly. So I just want to hold off on that for a little bit. And then the standard error of p hat this we established was p hat, and I use q hat over n. Now I can't remember exactly. Let me go back to last day. Oh, we talked about sampling, right? But here we said, okay, we worked through and got to, and then I said, well, I'm not going to tell you how we got the square root of p times 1 minus p over n, but that's just a fact. We accept it. And so one of the things that we'll need, right, is the standard error of the point estimate, whatever the point estimate is. And so in this case, the square root of p hat, and then remember q hat, I use q hat in place of 1 minus p hat, so I don't have to write so much. Okay, so if we have the point estimate and the standard error of the point estimate, the only other thing that we need is the critical value. And so the critical value, is the only thing that determines the confidence level or communicates the confidence level to our interval, right? Do you want to be 90% confident, 95% confident, 99% confident, right? And so that's the only thing. So the critical value is the only thing that changes with your confidence level. And so that's how we communicate to our calculation what confidence level we want to use. And so the critical value is the only thing that determines the confidence level of the interval, or the confidence interval, which I'm going to abbreviate CI, confidence interval. Okay, so you might have a guess, but we're gonna build up to it. So what we're relying on is that we have this normal distribution by the central limit theorem. So that's nice. Okay, and so what can we say? Okay, well, it's centered here on P, the population proportion, and then all our P hats are moving around here, around P, mostly hovering close to P, but it can happen that you get a small p hat or a large p hat, right? But what we want to do is, okay, the spread, right? So if we just think about it as the center is P, and then the spread, which used to be your standard deviation, right, is now your standard error of P hat is the spread, which is basically your sigma from before, your standard deviation. Oh, I made a mess. Maybe I'll do SD instead, right? Kind of the SD, the standard deviation equivalent. How about I say that? Because it's not the standard deviation, it's the standard error. The equivalent. So if we think back, okay, I've got a normal distribution, that's nice. And we've also got things like the empirical rule, so the 68, 95, 99.7 rule that says, okay, if I move out 2 standard deviations or standard errors, then I've captured the central 95% of the curve. And that's exactly what we're going to be doing. So here, the 95% confidence interval, which is our default, and I'll talk about why. But for now, 95% confidence interval means that we're going to move out 2 standard errors from our point estimate, right? Just roughly 2. We can use software to find that it's actually 1.96, but if you take a step back, then you realize that 1.96 is basically 2. And so if that's going to make or break your analyses, then you've got bigger problems, right? So we can use just kind of rough estimates. And of course, if we want to be more specific, then we would use Excel or some other software, right? And so in general, you're going to move down 2 standard errors of p hat and plus 2 standard errors of p hat for a 95% confidence interval, right? And so I'm going to say from the 68, 95, 99.7% rule, we know moving out 2 standard errors of p hat from p hat, or really just any 2 standard errors of whatever point estimate you have from your point estimate will capture roughly 95% of the curve. Okay. I jumped the gun. Therefore, the critical value for a 95% confidence level is going to be approximately 2. Right? So therefore, the critical value for a 95% confidence interval will be roughly 2. Okay. Technically, 1.96, which is very close to 2. So for us, right, we can focus on 95% confidence intervals and totally get away with it because the 95% confidence interval is the default. maybe I'll say the industry default confidence level is 95%. Well, I should clean it all up, but that one especially. So a 95% confidence level, it's been decided that that's an appropriate trade-off between precision and confidence, right? And so we need this trade-off, because what would I need to do in order to increase my confidence, right? If I wanted to be, well, let's go extreme. If I wanted to be 100% confident, what would I have to do? I'd have to go to negative infinity and positive infinity. And that's not very helpful at all, right? And so, so we have this trade-off, right, where I say, okay, how far is it to my house? It's, I think I changed my point estimate, 4 or 5 kilometers. Let's say 5 kilometers, plus or minus 10 kilometers. And you say, well, I'm very confident, but you say that's not useful to me, right? And so there's this trade-off between confidence and precision. And so 95% provides a trade-off between confidence and precision. To increase our confidence level, we need to increase our bounds. To increase our confidence level, we need to increase our bounds. Sacrificing precision. On the flip side, if I said, okay, it's 5 kilometers to my house, plus minus a meter, you would say, oh, how confident are you? I would say 10%. That doesn't help me either, right? So it's very precise, but I'm not very confident, so then it's useless. So it's this trade-off. So in general, we're going to use just the 95% confidence level. That's totally fine. If we were in kind of a traditional stats course, you know, we would talk more about different confidence levels and things like that. But heading out into industry, 95 is really the only one that you need. However, if you wanted to find a different confidence level, right? So that means you're going to have to adjust your critical value. What would you need to do? So to find the critical value for any other confidence level, we can use Excel. What would we have to do? We'd have to think, okay, so I've still got this normal distribution, that's great, centered on P, and let's say I want to make a 90% confidence interval. Forcing that central area, I guess it looks kind of off here, let's see here. There. I'm going to force this area to be 90%. Then what would I have to do? You want to find what negative Z makes this happen and what positive Z makes that happen. Now this Z, right, is going to be the critical value. And so often we denote Z star is the critical value. So I'm going to put a little star there. And so what would you have to do? You'd have to remember that, okay, I have the norm.s.inverse command, right? And so then I can give it the area to the left and it spits out the z that makes that happen, right? And so I could use the norm.s.inverse of, and I can't remember if it takes another, it's tough. I rely so much on starting to type in Excel and then it just kind of takes me there. Right. I'm like, oh, right. Yeah, I need this. And so I feel like it just needs the area to the left and nothing else. In this scenario, how would you find the area to the left of the value? You have two options, right? We want this one, the negative z value or the positive z value, doesn't matter. As long as you keep track of which one you're finding, right? I'd probably find the negative and then just drop the negative and use that as my critical value. And so then what would I do? I would say, okay, from here, the area to the left, it has to be, well, 100% underneath the entire curve, or 1 minus 0.9. So then I have 0.1 split between the two tails. And so now I have 0.05 and 0.05. Or if you wanted to force the positive z value, right, which is usually what I would end up doing, just because then I can just use it in my calculation instead of having to drop the negative and then use it. And so this area to the left is 0.95. So you could do, so norm.s.inverse of 0.05 gives negative z star. So then you'd have to drop the negative. You wouldn't even really have to. You would just have to kind of keep your head on straight because you've got the plus minus. So then when you do plus a negative, it becomes minus, and then you do negative minus a negative, it becomes plus. So it still works, and you can see it. Whereas if you use the upper one, norm.s.inverse of 0.95, it would just give the positive z star. So whichever one you'd like. All right, so as long as you're able to find the area to the left, then you can find the critical value. And so you can try it for a 95% confidence interval, for example, just confirm that it's close to 2 or 1.96. When I was learning this stuff, we had to memorize all the critical values. 1.645, 1.96, 2.576. You don't have to do that. It's terrible. Okay. So you can find, oh, hello? Sorry, hello? There was something, right? I'm not imagining. Oh, okay. Hey guys. Let's see here. Okay. All right. So, so you can find other confidence levels, and you can play around with that. I think in the exercise for Friday, you'll play around with that and see. But in general, we're just going to use a 95% confidence level, and that's good. Okay, let's see if there was anything else I wanted to. So for a good little while here, this critical value is going to be a z. That's going to morph into another value called a t, but we'll hold off there for a little bit. So for us now, the critical value, and that's why I keep it pretty generic here. It's going to change slightly, but the idea stays the same, right? It comes from some normal distribution or approximately normal, and then we can find how many standard errors I need to move out from my point estimate. Okay, how about an example? Now, the one I wanted to steal from, I'm gonna grab from, let's see here. Okay. Well, I've written all over that one. Let's see here. How about this one? Stealing from another course here. But that's okay. Let's make this bigger. So as an example, and this is an example of figuring out if we have a proportion question or a means question, which we talked about last day, that's going to be important. And so, of course, we're only introducing proportion, one sample proportion today. And so it has to be one sample proportion, but that's kind of nice. It's like having the solutions and you can work backwards, right? And so, which I always like. And so let's see here. Oh, and there's lots of typos in here that I don't like, but that's okay. So most commercial websites collect data. I can't help it. I have to there about their users' behavior. And use these data to deliver targeted content, recommendations, and ads. That's no surprise to us. To understand whether Americans think their lives line up with how the algorithm-driven classification system categorizes them, Pew Research asked a representative sample of 850 American Facebook users how accurately they feel the list of categories Facebook has listed for them on the page of their supposed interest actually represents them and their interests. Oof, so long. Pew Research is a famous research firm. And so one of the main things that we want to check for our normal distribution to apply or to work really is that we have to have a random sample or a representative sample. And so there's quite a bit of components here. So they asked a representative sample, and I'll put a little star here. Representative, presumably randomly sampled, right? We assume randomly sampled. It's one of the conditions. Okay. Now, this 850 has to be our sample size, right? We have a sample of 850 American Facebook users, and so 850 here tells us that N is 850. Whoops, that doesn't look like 50. The population that we're drawing from, right, are American Facebook users, which makes sense. I mean, we wouldn't be able, well, we wouldn't care about the general population because it's Facebook specific ads. And so of course we have to narrow it down to American Facebook users. Now, the problem is that means that our results can only be applied to American Facebook users, right? And so it's just nice to make a note of the population. So this tells us that the population is American Facebook users. Oh boy. So that's good. And so then we're told that 67% of the respondents, now of the respondents tells me that this is sample information, right? And so this is my point estimate for the proportion of the respondents, because remember, a proportion is the same as a percentage. You just have to multiply by 100, right? And it's also a probability, right? The probability of a respondent saying that the categories were accurate is 0.67 if I randomly draw an American Facebook user. So this tells me, and I'll use pink again because this is the information that we need. This is the point estimate, and I reverse the order that I'm saying it, but 0.67 is the point estimate. And I'm going to say, recall that a percentage is roughly a proportion, just divide by 100, which is a probability. Right, so these three P's are used interchangeably. Should capitalize that. So a proportion is a probability, and if you multiply it by 100, then you get a percentage. And so often, when we're talking about proportions, right, we report them as percentages just because it's cleaner and easier for our brains to read, and that's why we have them. Yeah. And so 0.67 or 67% of the respondents said that the listed categories were accurate. Now, for me, this next part, I'm just going to copy it, so I'm going to fix it a little bit. Instead of saying this, estimate, I would change it and I would say, construct a 95% confidence interval. Okay. And then, so I explicitly ask you to make a confidence interval. What we are doing is we're estimating the true proportion of American Facebook users who think the who think Facebook categorizes their interests accurately. Does that make sense? Who think Facebook categorizes their interests, maybe a that or something, I don't know. So here, what I would say is I would say construct a 95% confidence interval for the true proportion. Now, the true proportion tells me that I want to be talking about the population proportion, right? And so the true proportion here, the true is the population proportion. So we can use those interchangeably as well. Sometimes it just sounds better if you say the true proportion of American Facebook users, blah, 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 or the population proportion, right? Because that's what we're trying to capture, right? We're trying to capture the population proportion of American Facebook users who feel that this is accurate, right? And so, all right, what do we do then? All right, there are conditions to check. I'm gonna talk about them briefly, but they're not something that you have to worry about terribly. They take up a lot of brain space for not that much reward. They're gonna check out. And so I just want to outline them first. And I really can't remember if I did I talk about it? Let me see here. No, I didn't. So I will say here, before we construct our interval, okay. Before we construct our interval, we have to check that the conditions for the central limit theorem apply. Check that the conditions for the central limit theorem, the CLT, apply. There are two parts to the conditions. Okay, so the first part is independence. Independence is, well, are all my observations independent of each other in my sample? So here, what we're asking is, are observations in our sample independent of each other? Right. That's the condition that we need to check. Now, the main way that we do that is by randomly sampling, and then we can assume that they're all independent. And so random sampling ensures independence. Right. If you've randomly selected your sample, then you can assume independence. And so that's going to be your number one thing, right? You just jot down, yep, it was randomly sampled. In this case, what did we say? We had to phrase it a little bit differently. We assume it was randomly sampled because they tell us that it's representative, right? And so sometimes I think of these as just kind of stating your assumptions. Here are all the things I'm assuming. They're not necessarily given, but that's okay. So, or we assume the sample was randomly selected. The ultimate goal, though, is to have a representative sample, right? And so that's why we do random sampling. That's why we have to check for independence. There's kind of this one's optional. The second criteria, I'm gonna kind of skip it sometimes because it's just as ridiculous as what I'm gearing up for. So the second condition is, okay, so you want to have a large sample size, but not too large. And so then you want to restrict it to being less than 10% of the population. Because once you exceed 10% of the population, which in most scenarios is very, very difficult and highly unlikely, so it's not a problem. And that's why I skip it most of the time. But once you've exceeded 10% of the population, then you start to introduce some non-independence, right? You're more likely to have sampled siblings if you're researching, you know, some genetic thing, or you're more likely to sample people in the same house and things like that, right? And so then you lose that independence. And so n less than 10% of the population how can I summarize it? I'll just do a period. We want large sample sizes, large N, but not too large, because we might introduce non-independent observations. So that one's totally optional, and I skip it most of the time because it's usually something like this. So we've got a sample of 850 American Facebook users. Is that less than 10% of American Facebook users? Yes. Is that a large sample? Yeah, I think it's quite large, right? And so it's large enough, and we're happy with that. And so in this case, right, N equal to 850 is less than 10% of all American Facebook users. Oops. So that's good. So usually I skip that one. Oops. But so we said, okay, there's multiple parts to checking these conditions. So we have the independence condition, which I would say is the most important thing. The second part of the condition is the normality condition, or the sample size condition. The central limit theorem only applies if we have a large enough sample in order to detect the proportion that we're trying to find, right? So if I tell you, oh, I'm going to study this very rare disease, and I'm going to take a sample of 20 people, intuitively you would say, oh, that doesn't make sense, because you're not going to detect any people with this rare disease, or that's very, very unlikely. And so that becomes the problem. So if you've got a small proportion that you're trying to detect, then of course you need to increase your sample size. And so our sample size must be large enough, must be large enough to detect whatever proportion that we're trying to find, to detect the proportion we're trying to find. Now, for a confidence interval for one sample proportions, how we check that. So a confidence interval for one sample proportions, or one sample proportion rather than plural, how we check it, and that's going to change depending on what we're doing, is we need to have at least 10 successes and at least 10 failures in our sample. We need to have at least 10 or I'm going to emphasize observed successes and at least 10 observed failures in our sample. Meaning that the absolute minimum sample size that I could be working with is 20, assuming that the proportion is 0.5, right? A 50-50 split. And so if I change the proportion, then I'm gonna have to increase my sample size. And so for us, how we're gonna check this is, can't remember, it's a lot I can't remember. If, you know what, I'll just say, let X, just in case I didn't introduce it last day, which I feel like I didn't, let capital X be the number of successes. All right. Recall that P hat is X over N, right? The number of successes over your sample size. So then if you want to have at least 10 successes, observed successes, well, then X has to be greater than 10. So depending on if you have the number of successes, so some problems give you, 45 out of 50 respondents said this, right? And so then you have the number of successes over the sample size, but most of the time we'll have our P hat and we have to solve for X roughly. And so then X is N times P hat. And you had to kind of sit down and I asked you how many successes were there in this example, you would arrive at, well, 67% of 850, right, is 850 times 0.67, right? So in our case, X is 850 times 0.67. My trusty calculator. 150 times 0.67, I get 569.5. I'm not going to round it just because it is due to rounding the 0.67. And so I'm just going to keep it. But what I'm checking is that this is greater than or equal to 10, and that's a good thing. So I have at least 10 observed successes, and the flip side was that I have to have at least 10 observed failures. Now, since I have X, if I know that 569.5 out of 850 were successes, then of course the remainder would have to be failures. And so we can also check that N minus X, which is 850 minus 569.5. Let me 280.5, which is also greater than or equal to 10. And so this is checking that we have at least 10 observed failures. Alternatively, what you could do is you could, or N times Q hat, right? Q hat being the proportion of failures, right? And so either way has to be greater than or equal to 10. And you would find the same thing. And I'll just do it here. 1 minus 0.67 is 0.33 times 850. Hopefully it's the same, yeah. 280.5, which is, scoot this over. Wonder what that was. Just greater than or equal to 10. Oh, it's snowing again? Come on. Soon, it'll be done, I hope. Okay, so a lot of work, like I said, and if you had to memorize these things, then that's especially a lot of work. Now, your quizzes are open book, so I might, ask you, hey, what are the conditions that you have to check? And and then you have to know how to check them. But besides that, once you have checked these conditions, then you're allowed to proceed. So we can summarize by saying the conditions for the central limit theorem are satisfied, or something like that. And now we can proceed. So now we can make our confidence interval. And let me see. Okay. We do. So our point estimate plus minus some critical value times the standard error of the point estimate. Right, the point estimate has some spread, and in our case, our point estimate is p hat, and our critical value is determined by a z, and I'm going to use a z star just to show that, hey, this isn't something that we've calculated necessarily, we just found it using software. Times the standard error of the point estimate, which is the square root of p hat q hat over n. Aha. We also said that, all right, for a 95% confidence interval, that was quite a while ago, but I think we wanted a 95. I don't see why I would mix things up. Construct a 95% confidence interval. And so usually we would use software and use the more accurate value. But here I'm going to say Z star for a 95% confidence interval is roughly 2 or 1.96. Either one is going to work. Okay. So for me, I think intuitively using 2 is a little bit easier, because then you've got that connection between 95% 2, right? And then anything else you can use software, or maybe you've already committed 1.96 to memory, that's fine too. Sometimes I'll give you the critical value to use, right? I'll tell you to use 1.96 or 2, but in general, 2 is fine. So let's see here. What was our point estimate? Our p hat was 0.67, right? And so here, p hat was 0.67. P hat again, well, that's still 0.67. Q hat is 1 minus 0.67, which is 0.33. And N, what color do I use here? N was 850. So just like that, we have all the components. So now it's a matter of plugging those values in and seeing where we get to. So 0.67 plus minus 2 times the square root of 0.67 times 0.33. Oops, need to extend this. Divided by 850. We have to solve the square root first. I'm going to multiply, then divide, and then take the square root. And then I'm going to pause and put those values in. In fact, maybe this very first time, I'm going to write out every step. It's a lot. You don't have to do that. But if it's been a while since BEDMAS, then maybe that's a good thing to review. I'm always curious if everyone knows what BEDMAS is, the order of operations, or PEMDAS.
No, I think BEDMAS is pretty famous.
Yes, you think. I guess in the States, they use PEMDAS a lot. Parentheses, exponents, multiplication, but I like BEDMAS better because that's what I'm familiar with. So I'm going to start with a 0.67 times 0.33. And again, you don't have to show all these steps, but I just want to do it so you can see how the calculation unfolds. Divided by 850. Times the square root of scientific notation. Okay, 1, 2, 3, 2, 6, 0, 1, 1, 7, 6, 4, 7, 1. Whee! Let me just see. 1, 2, 3, 4. Okay. I got to figure out how to set my calculator to not.
Convert to scientific.
Yeah, it just
Yeah,
does scientific
mine also
notation.
convert to-
Yeah, which is convenient, but sometimes not really. That's okay. It's going to get bigger once we take the square root. Take the square root of a small number and it gets bigger. 0.67 times plus minus 2 times 0.016. 12816316. This here is the standard error of p hat, right? And so here, this is the standard error of p hat. Right, so that's our spread. It's essentially our standard deviation of p hat. So now I want to move out 2 of these, right? 1, 2, 95%, so times 2. So I get 0.67 plus minus 0.0322563. 2633. I can't stop. Sometimes I try to be cool about it, but I can't. Okay, this, once I've multiplied by my critical value, this is called my margin of error. So in a lot of research papers and things like that, and scientific journals, then you're going to see the margin of error. So this is the margin of error. Oops. Depending on your field, it might be MOE or ME. Doesn't matter as long as you recognize it. And so that's going to be your buffer, right? And so plus minus the margin of error. Right? Now, one of the things that we can do is, well, a smaller margin of error means what? At the same confidence level, it means that I can be more precise, right, around my point estimate. And so sometimes before we conduct a study, before I collect a sample, I might set out and say, hey, I want to force my margin of error to be 2%, right? So 0.02 instead of 0.032, blah, 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 right? And so I want to reduce it a little bit. Then what I can do is I can reverse engineer all this and say, I'm going to force this to be 0.02. And then this stays the same, this 2 stays the same. And then you'll be able to find what sample size makes that happen. And that's a kind of a reverse engineering problem, right? But then you can say, okay, in order to force my margin of error to be 2%, right, or 0.02, then I would need a sample size of this size. So that's kind of cool. I guess not really what we're doing right now, but I will make a note. And so we can calculate the sample size necessary to achieve a desired margin of error by solving for n. So in my calculation, usually I would call this the margin of error. I would call it m in my calculation. But I've kind of derailed, so let's see here. Let's go back to our interval. So that's just kind of a fun thing that we can do, and it's a way of figuring out what sample size you might need. Right? Okay, so we've got this 0.67 plus minus 0.032, blah, blah, blah. Right, and so we're going to go down 0.0322, blah, 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 and we're going to go up 0.0322, blah, blah, blah. And so what we end up having is we end up with this interval, and because we're using, you know, rounded values and things like that, we have to use round brackets because it's not the exact value. But what you want to do is you want to do 0.67 minus 0.032, blah, blah, blah. Now, most scientific calculators have a store function. I would store this long value so you don't have to type it in all the time. So I get 0.67 minus that thing I just stored, and I get 0.6377436737. Too long. Then separate it by a comma, right? Because it's an interval and you want to make sure that you go from your lowest part to your highest part. The interval from the highest part to the lowest part doesn't exist, right, on a number line. And so that's important. But then I want to go 0.67 plus that thing that I have stored. So 0.7022563,263. It's always nice to show all these decimal places and then reduce it, right? And then simplify. Remembering that a proportion is a percentage. So if you wanted to report these as percentages, that's totally fine. 63.77% and 70.23%, that's fine. Oh gosh. Snow. Okay. It's exciting in like November. Not so much now. We're over it. Okay, so I'm going to reduce this to 0.6377 and 0.7023. Or 63.77% to 70.23%. Making sure that you keep the same number of decimal places. So usually I just kind of scope it out and figure out what an appropriate number of decimal places is, where I can showcase the activity without being so overly precise. Which makes no sense because I started from 0.67, which is a rounded value. So, but 4 decimal places is usually safe. And so whether you want to interpret this in terms of the proportion or as a percentage, they're the same, right? Just remember which one you're talking about. Now, once we have this confidence interval, the other half of the problem is interpreting this confidence interval. So this calculation is not difficult in any way, right? And so especially if you have Excel, then you're off to the races, right? So the calculation is not hard. The hard part is the interpretation. And so let's see here. we must interpret the interval. That's our job, right? We're not here to learn the math of calculating a confidence interval. Well, we are, but that's not our job, right? Our job is interpreting this thing and explaining what it means. Now, we're just starting. And so one of the problems with confidence intervals is there are so many ways that you can misinterpret it. Okay, and so for the beginning here, and potentially always, I want you to use this fixed wording, which will always apply to any confidence interval. Okay, and it's going to take some practice, a little bit of memorization, but once you have it, then you're good. So I'll say always use the following sentence structure. So many colons. How about this? We must interpret the interval exclamation mark. It's important. So we're going to use this sentence structure and potentially you'll use it forever, and that's totally fine. It's totally safe. And just remember that there are so many ways that you can misinterpret it. So don't try to kind of make it fancy. Just stick with this sentence structure. So we are some percent, so whether you made a 90% confidence interval or a 95% confidence interval, right, doesn't matter. So we are some percent confident the interval from blank to blank, and then the arguably the most important word here is captures. Captures, and kind of confusingly blank. Captures what? Well, captures the parameter that you're trying to capture, right? That population thing that you're trying to capture. So filling in just kind of a 95% potentially, so we're 95% confident the interval from some lower bound to some upper bound captures the parameter. So I'm going to apply this to our example, okay? But I will make a note first that the parameter, you're just going to reword the question as an answer. Reword the question as an answer. I'll show you what I mean. So it's going to be long and tedious, but not hard. Okay. So I'm going to grab, oh, where was it? Long time ago. Copy. Grab the question. Okay. The question was construct a 95% confidence interval for the true proportion. And so that's the parameter, the true proportion of American Facebook users who think Facebook categorizes their interests accurately. So now we have an interval. In fact, we're 95% confident that the interval from, let's say, 0.6377 to 0.7023 captures, right? Captures the true proportion of American Facebook users who think Facebook categorizes their interests accurately, right? And so you just reword the question as an answer, and then you've got it. So in our case, we would say we are 95% confident the interval from, now I have a decision to make. It's totally fine to use either of these, but because I want to talk about the true proportion, I have to use the proportion version. If it said the true percentage, then I would use the percentage, right? Or you can change proportion to percentage, but you'd have to remember to do that, right? Otherwise, it's not quite right. From 0.6377 to 0.7023, I think it was, yes, captures the true proportion of American Facebook users who think Facebook categorizes, long and tedious but not hard, categorizes their interests accurately. Oops. Right. So here, that's what changed. The interval from here to here captures the true proportion of American Facebook users who think Facebook categorizes their interests accurately. Nice. And doesn't that sound cool? Huh? Wow. Okay. I do want to make a note here, right? This is why we had to use the proportion, right? Or you can change it to be the percentage. Ah, okay. There you have it. Confidence intervals. So we'll do confidence intervals for different point estimates, but we'll start with this one and build up. So we'll start hypothesis testing on Wednesday. If you have any questions, let me know. Otherwise, see you then.